Okay, everyone. Today we're starting a new unit called stoichiometry. I know it's kind of a complicated word, but it basically involves just your regular dimensional analysis. Okay, there is not going to be any uh, math that is not dimensional analysis in stoichiometry. So if you have your dimensional analysis down, which most of you do, okay, you should have no problems. It's basically going from one type of thing to another type of thing using dimensional analysis. Okay, so um, stoichiometry, I told you that it was dimensional analysis. What this actually means is, let's say you have the amount of a reactant, okay? Like, let's say I have a reaction where water is being made, and I can tell you, so hydrogen plus oxygen make water, right? That's a synthesis reaction. We talked about that before. Let's balance this out. So you have hydrogen and oxygen making water. If I tell you that I have 50 grams of hydrogen using this principle of stoichiometry, you can actually figure out, once I teach you, how many grams of water are we making if we start out with 50 grams of hydrogen. So you haven't done this kind of thing before, right? What you've done is you have learned how to convert 50 grams of hydrogen to moles of hydrogen, but we're going to extend that a little further and see how can we start with the mass of one reactant and then predict how much of the product we'll end up getting, because that's the actual useful part of chemistry, right? Before a reaction you'll have the ingredients or the reactants for the reaction, but if you know the masses for your reactants, you can then figure out, oh, if I have this much and this much, then I will get this much water. Like saying, okay, a cup of flour, a cup of water, some number of eggs and oil or whatever makes one cake. You are trying to figure out, if I have 50 grams of hydrogen and 50 grams of oxygen, let's say, how much water will I actually end up getting? Okay, so predicting the amount of product is really a useful skill in chemistry, and it's applied all over the world all the time in real time. Okay, so you can compare reactants and products to each other very easily using this dimensional analysis principle. Okay, so here are the things that you need for stoichiometry. You need um, a balanced equation. You cannot do stoichiometry with a balanced equation, which is why we learned how to write equations, we learned how to balance them. These are all skills that you're going to be applying for this unit. Okay, then coefficients that we use to balance the equation, like the numbers that you put in front of reactants and products, those can be compared or read as moles of that substance. Okay, this is super important. Coefficients do not indicate the number of grams. So let's say in the previous one I had 2H2 plus O2 goes to H2O, 2H2O actually. These are coefficients, right? These are my coefficients. There's a 1 here, and these can be like 2 moles of hydrogen, 1 mole of oxygen, 2 moles of water, but these can never be read as 2 grams, okay? Coefficients cannot be grams, okay? They cannot be grams. I can say I have 50 grams of hydrogen, but the 2 is not the mass, it's just the moles. So you have 2 moles of hydrogen to 1 mole of oxygen to 2 moles of water in this reaction, okay? Now, uh, here are all the different ways you can read a reaction. You can talk about atoms. You have 4 atoms of iron. You have 3 molecules. Remember, oxygen is a covalent compound. That's why you use molecules. And iron is just pure element. That's why there's atoms here. These are all the different particle units, okay? And then 2 formula units of iron trioxide, because that's an ionic compound, okay? Or you can read it as moles, which is what we're going to be doing this unit. You can say 4 moles of iron to 3 moles of oxygen to 2 moles of iron oxide. That's easy, right? Because if you say everything is just moles, you just have to use one thing to describe all the coefficients, okay? But look, if you try to use grams, the grams are very different, right? This is the molar mass of 4 atoms of iron. This is the molar mass of 3 molecules of oxygen. And this is the molar mass of 2 units of iron 3 oxide. So masses are not like a comparable thing in the coefficient or in the use of coefficients, okay? But you'll see the law of conservation is here. The mass of reactants is equal to the mass of products because we know that mass must be conserved, matter must be conserved. So the mass of reactants and products after the reaction is over, the products are going to weigh the same as the combination of the reactants. Okay, so let's um, let's look at what a mole ratio is. So a mole ratio is what you need to write for dimensional analysis or stoichiometry involving dimensional analysis. Okay, so here is an equation that's been given to you. You have 3 silicon with 2 nitrogen going to trisilicon tetranitride. Okay, so the coefficients can be read as moles, right? There's 1 here. Since there's nothing there, we assume there's a 1. Okay, so the coefficients can be read as moles, so that means you have 3 moles of silicon for every 2 moles of nitrogen and 1 mole of trisilicon tetranitride. Okay, so that means there's a 3 to 2 to 1 ratio in the whole equation. But you can take 2 of those components and write them as a conversion factor. Let's say I want to look at the relationship between just silicon and nitrogen. That means I have 3 moles of silicon for 2 moles of nitrogen. I can write that as a ratio. I have 3 moles of silicon for 2 moles of nitrogen. It can be written in this way, where 3 moles of silicon is over 2 moles of nitrogen. Or you can switch it and write 2 moles of N2 over 3 moles of Si. They're just ratios, okay? So that's the ratio between these two things. What if I wanted to look at the ratio between, let's say, silicon and the product? These two, I can either write 3 silicon on the top, 3 moles of silicon, and then the Si3 and 4 on the bottom, 1 mole of that. Or I can switch these. I can write a new conversion factor with 1 mole of Si3 and 4 on the top and 3 moles of Si on the bottom. You can also look at the relationship between the second reactant and my product, nitrogen and Si3 and 4. So I can put the 2 moles of N2 on the top and then Si3 and 4 on the bottom. Or I can flip this and I can write 1 mole of Si3 and 4 on the top and 2 moles of N2 on the bottom. Okay, so basically you're just taking each of the components and putting one over the other in different permutations. Okay, you can just have this over this or this over this. You can have the relationship between this and this, where N2 is over this or Si3 and 4 is over this. And then you can have something where you're comparing Si and N2, where N2 is over Si or Si is over N2. Those are all of the mole ratios. So these are all called mole ratios, and those are the mole ratios you can write for a chemical equation that is balanced. All right. So the important thing about mole ratios is mole ratios actually, they are the ones that help you do the dimensional analysis. What is that handwriting? Analysis for um, stoichiometry. Okay, mole ratios are super important. They allow you to go from moles of one thing to a moles of another substance. So if I want to go from moles of silicon to moles of the product, I would use a mole ratio and do dimensional analysis to do that. Okay, so let's actually do a practice question. Here's my balanced equation. I have 2 moles of SO2 reacting with 1 mole of O2 and 2 moles of H2O to produce 2 moles of sulfuric acid. So I have 2 moles of sulfur dioxide, 1 mole of oxygen, 2 moles of water combining to produce 2 moles of sulfuric acid. Okay, so I can compare any one of these reactants and products to each other. We have a 2 to 1 to 2 to 2 ratio here. Okay, so based on what the question is asking, you have to pick which two things you are comparing. So let's examine the question. Okay, the question is asking you how many moles of sulfuric acid. So the first thing I'm going to compare is this, are produced from 12.5 moles of SO2. So the question is asking me to compare sulfuric acid and SO2. How do you know that? It's in the question. Okay, sulfuric acid and SO2 are the things that are being compared in this question. Okay, so we are looking at the relationship between this and this. Now, remember mole ratios that we just talked about? We should write the mole ratios that represent the sulfur dioxide and H2SO4. So remember, you can put SO2 on top and H2SO4 on the bottom, and the other one will have H2SO4 on the top and SO2 on the bottom. So I have 2 moles of SO2 over 2 moles of H2SO4, or the opposite of that, 2 moles of H2SO4 over 2 moles of SO2. There we go. Those are my conversion factors. This is my first conversion factor. This is my second conversion factor, or in other words, my mole ratios. Okay, so the mole ratios, you only have to use one of them to solve this problem, and the one that you pick will depend on which compound you're starting with and which compound you want to end up with. Remember, one of the units must get cancelled out in dimensional analysis, so it just depends on which unit needs to get cancelled out, like what needs to be on the bottom. Okay, so let's read the question again. I'll pick a different color. Let's do red. Okay, so there's too much red on the slide. Let's do light blue. So it's asking how many moles of sulfuric acid. So that means we have to end up with moles of H2SO4. Whoa. Moles of H2SO4. It's all right. The answer is already there, but I just want to show you how the work is done. Okay, so you have moles of H2SO4. That's what you want to end up with. We are starting with 12.5 moles of SO2. So 12.5 moles of SO2 is what I'm starting with. So now it's regular dimensional analysis. You need your multiplication sign, your line, and equal. Okay, now let's look at the setup. We want to cancel out moles of SO2 and we want to end up with H2SO4. So we need the conversion factor with SO2 on the bottom and then H2SO4 on the top. So I'm going to write 2 moles of H2SO4. That's our mole ratio that we wrote, okay? And then 2 moles of SO2 on the bottom. Moles of SO2 cancel out. 12.5, let me just get rid of this. Moles of SO2 cancel out. 12.5 times 2 divided by 2 just gives us 12.5. Okay, now you might be like, Mrs. J, isn't it obvious that you have a 2 to 2 ratio, so it's a 1 to 1 ratio? Yes, it is. Okay, if you wrote 1 mole of H2SO4 for 1 mole of SO2, that's totally fine because 2 over 2 cancels out to 1. Okay, but it's just this question. I don't recommend you do that for as a practice because it's really easy to get confused because it doesn't always cancel out, and then we just forget that there's a number on the denominator, usually because the number on the denominator has always been 1. So remember, you multiply by 2, you divide by 2, it's the same thing, you get the same answer, but just write down the coefficients as they are in your mole ratio as a practice. Okay, so let's look at the second question. The second question is asking us to compare two different compounds. So how many moles of O2? So now we're comparing O2 there's O2, I'll do a circle instead of a square, are needed to react with 12.5 moles of SO2. So it's asking us to compare O2 and SO2. How do we know? Because the question has O2 and SO2. Those are the two things being compared. So I'm comparing this and this, okay? So let's look at the ratio of moles. We have 2 moles of SO2 for every 1 mole of O2. So let's write the mole ratios for that. We have 2 moles. It's super annoying. I don't know what keeps happening today. All right, we have 2 moles of SO2 for every 1 mole of O2. Okay, or the opposite of that, we have 1 mole of O2 for every 2 moles of SO2. Remember, mole ratios is just putting this over that or that over this. Okay, so 2 moles of SO2 over 1 mole of O2, 1 mole of O2 over 2 moles of SO2. 1 mole of O2, because if there is no coefficient, that means it's 1, right? So let's do the problem now. They want us to end up with moles of O2. Okay, so that means we are looking for moles of O2 and we are starting with 12.5 moles of SO2. Multiplication sign, line, equal sign. Now let's figure out which mole ratio or conversion factor we have to use. I want moles of SO2 to cancel out, so I need the one with moles of SO2 on the bottom. That means 1 mole of O2 on the top, 2 moles of SO2 on the bottom. Moles of SO2, moles of SO2 cancel out. 12.5 times 1 divided by 2 gives me 6.25 moles of O2. Okay, so that means if I react 12.5 moles of SO2, I need to also react 6.25 moles of O2 based on the ratio in which they combine. Okay, so for every 12.5 moles of SO2 that's reacting, 6.25 moles of O2 will also react. So mole ratios are used just to do stoichiometry and dimensional analysis, where you start with the moles of one thing and you go to the moles of a different thing. And it could be any of the components in the reaction. You just have to read the question carefully to figure out which two things you are comparing. Once you know the things you're comparing, all you have to do is write down the mole ratios and then plug in the correct one into your dimensional analysis equation as a conversion factor. Okay, so that's it for today. I'm going to send you a few questions.